give us a reaction with an unknown equilibrium constant. Then they give us two other reactions, a known constant.
Sounds like we're using Hess's law for this one.
It very much is looking like a Hess's law problem where you're adding reactions together. So the question is, how can I take these two to make that overall reaction? It's very much what Hess's law called out. If we look at the two reactions, the first reaction, as we have it, this one here, if we look at this one, CO, this is 2H2 going to CH3OH. If we look at that one, we could keep that in the reaction because the CH3OH is our single product here. Let's keep that one as is. Keep the K3 value the same.
I'm sorry, what are we doing with this problem?
We're adding those two reactions together to get the reaction we don't know the K for.
Okay.
If we look at the second reaction, in order to, this reaction here, in order to get it to work, we have H2 and CO2, which are actually in the front of this reaction here. So we're going to have to spin those around to get those to work. Take this reaction in the opposite direction. I spun that around because I flipped the reaction around. Remember, the rule says if you flip a reaction around, we have to change the K2. K2 now is now 1 over 1 times 10 to the minus 1 times 10 to the 5th. So I reverse reaction and take the inverse of it. I add these two reactions together. CO's cancel out. CO2 plus 3H2 is the CH3OH and water, which is what we wanted. Now, because we took two reactions, we added them together. Rule says that I take the two equilibrium constants and I multiply them. First one, 1.4 times 10 to the 7th, multiplied by the second, 1 over 1 times 10 to the 5th. When I do that, the new equilibrium constant is 140. So if you're given a problem like that, the key is, just like Hess's law, you're going to manipulate these equations to get the overall equation. Most commonly, you're going to flip into something. They have to multiply it. Most commonly, you're going to flip it. Just remember, if you change the equation, if you flip it, as we do here, you have to take the inverse of the coefficient. And when you have all that, if you multiply your new equilibrium constants, you can get what the equilibrium constant is for that reaction is written. You can see that initially, these two as written, very product favored, very strong reactions. Still, even though we flipped one around, you still get a decent value for K that would be product favored. Not as high as they were to start with, but they are still decent values, very much like Hess's law. This time, instead of using delta H that you're adding together, you're using the equilibrium constant that you're bringing together. When we look at equilibrium constants, we said that we talked about them being in the units of concentration. One thing about equilibrium usually, when we deal with it, our concentrations are in, so we use the bracket form, it's usually in moles per liter. That's one of the ways that we can express concentration. But we can also use partial pressure. If we're using a gas system, partial pressure is an equal way to express it. If you have an equilibrium expression and all your concentrations are in moles per liter, they will usually call the equilibrium constant K sub C, indicating that it's concentrations in mole per liter. If, however, you're doing a problem and the concentrations are in partial pressure, because it's an all gas system, usually they use ATM, and the equilibrium constant is now K sub P. It matters which one you're in. There's a relationship that relates equilibriums measured as partial pressures versus those found as concentration. That expression, book goes through the long derivation. Not worried about the long derivation. The equilibrium constant in partial pressures equals the equilibrium constant in moles per liter, except the only thing different, R is a gas constant, which is 0.0821. T is the temperature in Kelvin. These two can be equal to each other. It depends on delta N, what we raise this to. Delta N is looking at the coefficients. That is the change in the gas number product to reactant. So this is number of gas products minus number of reactants. That is the coefficients. What's in front of anything that has a gas, I'll show you the example. We subtract them to find the difference. If there's no difference, if it's the same number, then that whole thing would be raised to the 0 power, and that whole thing collapses, and then the two numbers are the same. Let me show you what it looks like on the top.
Excuse me, Professor.
So here you have an all-gas reaction. They tell you that the Kc for the reaction is 14.3. Yep.
Yeah. So which R
Is that one? That says they measured everything in mole per liter, and that's the equilibrium constant they got. They want to know what is Kp. So we can use the expression. Before I even put any of the numbers in, let's look at the coefficients. They ask us to find what are the total number of gas molecules, coefficients, products minus reactant. Well, there's a 2 in front of this. There are 1s in front of each of these. So there's 2 total on this side, there's 2 total on that side. So the delta N is 0. There's no differences. 2 coefficients for gas molecules on one side, there's 2 on the other. Good.
Which value of R are we using?
Oh, 0.0821, the standard. Okay.
How come we're not like we did with other chemistry problems when we're working with reactions, how come we're not doing like the 1 times the small 2? Like,
You're looking at just the coefficients in the front. Not how many we're looking at how many H2 there are. There's one H2, not how many hydrogens there are, because there's two hydrogens. We're looking at just the number of molecules. There's one molecule of this, one molecule of this, two on this side. They're all gas phase. We just look at, not breaking it apart, just how many there are in the whole thing. Because the delta N is 0, that means I would raise this whole thing to 0, and anything raised to the 0 power is 1, which means that the Kp and the Kc are the exact same thing. The Kp in this case equals the Kc, which is the 6.2. Doesn't change.
How could delta N be 0 for that?
2 on this side,
Oh,
2 on this side. So 2 minus 2. There's the coefficients here. There's a 1 in front of this. There's a 1 in front of this. These are both gases. They add
Oh,
up
yeah.
to 2.
it's balanced, okay.
Exactly.
Well, anytime an equation is balanced, the delta N is always 0?
Be careful when they give these problems. When you're doing this count, just count the species that are marked as gases. If there was something else in there, something in the liquid form or solid form, don't count their coefficient. They're just looking for the species that are gases.
Just gases, okay.
In this, and we're doing Kp to Kc.
Okay.
Again, your book walks through how they got to that equation, the Kp-Kc equation. They take about a page and do it. I'm not worried about the derivation. It's not worth the time to dig into that. Again, we spoke that every time you write K, K is unitless. There are no units to K, it's simply a ratio. The one thing we have to look at is most of the initial reactions in this text talk about gas reactions. Now we get to the point we talk about what we call heterogeneous equilibrium. That is what happens when it's not just gases going on. This is much more going on. In a heterogeneous equilibrium, the easiest way to look at it, let's look at a reaction, talk about what makes the cut and what doesn't. We have here a reaction between CO2 and water producing hydrogen ion and the bicarbonate ion. We want to describe what happens, but if we look here, we have 3 phases involved. We have gases, we have aqueous, we have liquids. The rule that's going to come down is that pure liquids, that is anything that has an L in it, and pure solids, anything signified with an S, don't make the equilibrium constant. They're simply ignored. Not included in the equilibrium constant. Now, reason being, your book does what most do, and they do a pretty good job here. There's really 2 things that go on here. If you have a pure solid sitting in a reaction, a block of a solid, as the reaction goes on, some of that solid may react. It may turn into, let's say, a gas. The reason we exclude the solid, for every bit of that solid that we lose, it loses some bit of mass. It's trading over into a phase.